Okay, today we are starting Chapter 2. Chapter 2 is the introduction of one of our we have two big ideas in calculus. This is the first, which is the derivative, which basically, if you just keep this in mind, derivative is the slope of a curve at a particular point. We started talking about this a little bit in the beginning of Chapter 1 with our introduction. So once again, what we're talking about here is finding slope of the tangent line at a particular point. So if we're looking at this right here, we're talking about the slope of that line roughly, okay? So as we said before, we can't use sort of standard means because we're going to get a 0 over 0. This is the whole tangent line problem. So what we need to do is basically we need to create a second point. So we're going to create a second point. So C is just some constant, some value that we don't know yet. So we're going to come up with a second point, so we're going to call it C plus delta x. By the way, if you want to use H here instead of C, that's up to you. Or excuse me, H instead of delta x, that's up to you. I have no problem with that. So we get our second point, okay? And we start with, so this would be, output would be f of c plus delta x. Now, what we're going to do is, we're going to find the slope of this secant line. So this is going to be the slope of the secant line. And we're going to use that ultimately to get the slope of the tangent line. Secant line just means connects in 2 points. Tangent line means it connects in 1. Okay, so rise, so that will be f of c plus delta x minus f of c over c plus delta x minus c. So what happens all the time here is this is going to simplify and we're just left with the delta x in the denominator. So the slope of our secant line is f of c plus delta x minus f of c all over delta x. Okay, so when we started Chapter 1, we used this to approximate the tangent lines, and what we did was we chose delta x's that were smaller and smaller and smaller and smaller. So we can approximate this by choosing a delta x that is smaller. So we can do an approximation. Let's write that. So we can approximate the slope of our tangent line by choosing relatively small. And sometimes, you know, if we're looking at a table of values or something like that, we can only get as close as the table will allow. But you know, we typically go for whatever's the smallest thing we can get. If we did have use of an equation and we were approximating, we could choose values for delta x like 0.1, 0.001, et cetera, et cetera, et cetera. Okay, now, how do we get the exact? So the way we get the exact is, and this is the slope, the actual slope, not the approximation, the slope of the tangent line at x equals c. This is also referred to as the derivative of the the derivative of f at x equals c. So when we say the derivative, we are saying the slope of the tangent line. Okay. And that would be just by limiting delta x to 0, and that was the whole point of learning limits, is they give us the tools to do the things we need to do in this class. Limits give us the tools to do our two big ideas, the first being slope of a tangent line, the derivative, and the second big idea will be area under the curve, which is called the integral, which we'll get to later in the course. Okay, so the notation here is f prime of c. Okay, so this is f prime of c is equal to the limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x. Okay, so this is our definition of derivative at a value c. So now we're going to go ahead and do some examples with this. Okay, so once again, here is our definition of derivative at a value c, f prime of c. The limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x. And we are going to use that to find the tangent line to f of x equals x squared minus x plus 1 at point x equals 1. One thing I want to say about this, there is a trick to do this. I don't know if you learn it, that makes this quite easy. We'll be learning it early in this chapter. When you're asked to use the definition of derivative, which is true for all 2.1, you have to go through this algebraic process that I'm showing you here, and it's very important you show it step by step. Every step has to have all the parts. You can't just work on the numerator. You must see all parts. It's basically like a proof. Okay, so if you're in doubt as far as what you should show it all. All right, so let's go ahead and get working here. So we have so let's plug this in. So what we're trying to find is f prime of not c, but 1, which is equal to the limit as delta x goes to 0 of f of c, or f of 1 plus delta x minus f of 1 over delta x. Okay, so now let's plug this in. So this will be the limit as delta x goes to 0. Everywhere I see an x, I plug a 1 plus delta x. So this will be 1 plus delta x squared minus 1 plus delta x plus 1 minus, and then let's plug 1 into this, right? F of 1, that's going to be 1 minus 1 is 0, so that is 1. So this is just our f of 1 over delta x. Okay, so we have to do some simplifying here. I'm going to start by multiplying this out. You do this any way you like. If you want to use the old CPM box method, feel free. These are not the type of things that I'm going to concern myself with in this course. So 1 plus, and this will be 2 delta x plus delta x squared minus 1 minus delta x. And then you'll notice here this is just going to zero out, and this is all over delta x. Now, if we've done this correctly, and this is an easy check, everything that doesn't have a delta x should cancel. Now, when we cancel these things, as I said in class, don't go scratching these things out. Just a single slash through it is good enough. That's going to work. Okay. Oh, you know what I forgot? I forgot the limit, which is very important. Without the limit, it's not the derivative, and you will lose points. So make sure you have the limit as delta x goes to 0. Okay? Very important here. All right, so let's keep going. So now I can factor out a delta x out top because every term has a delta x, which leaves me with 2 plus a single delta x here minus delta x. So that'll be minus 1. Okay, over delta x. Now the whole point is we have that 0 in the denominator, which now is removed. Now there's nothing holding back. I can plug 0 into this. So I'm going to get the limit as delta x goes to 0 of 2 plus delta x minus 1. So I get 1, and that is the slope of my tangent line to this function at x equals 1. Okay. Okay, so now we're going to generalize this process, and we're going to talk about the derivative function of f of x. All we mean by the derivative function is we're not looking at a particular value. Last time we were looking at a particular value, x equals c. Here we're talking about x being any value, so we're talking about a variable situation. By the way, in this class, when we use letters like A, B, and C, kind of letters at the front of the alphabet, that typically is going to mean that we're talking about an unknown that we just don't know, but it's a constant. Okay, if we use letters like X, Y, Z, things like that, those are variables. Those are ever changing. In this class, which is probably not true of past classes, it's very, very important we keep those two things separate. Okay, so when I use a letter like x, I'm saying a variable, we're going to come up with a function here. Now, you're going to see this is exactly the same as what we did before. We're interested in the slope of that tangent line, but for any particular x value. So we're going to do this the same way. We're going to come up with a second point. Okay, call it, surprise, surprise, x plus delta x. And so we have the output here is f of x. We have the output here, which is f of x plus delta x. All right, so we start with the slope of the secant again, which is going to be f of x plus delta x minus f of x over delta x. So like I said, there's a subtle difference here. Now, as this stands, this is slope of the secant line. We want the slope of the tangent line, but as a function. So what we're going to do is we're going to slide those 2 points infinitely close, and this secant line limits to the slope of that tangent line. And this is what we refer to as the derivative function of f of x. And of course, what you're seeing here is exactly the same as what we were doing before, except now we have an x. So let's go ahead and go back to the problem I was just working on, which is, nope, let's not. Okay, so let's go ahead and do this. I'm going to erase to give myself some room here, and then we'll do an example using the definition of derivative here as a function. Okay, so now we are going to do the derivative function of f of x, which is equal to 4x squared minus 5x, okay? So once again, when we're doing this definition of derivative, it is very important that we show all of the steps, all parts of all the steps, okay? So what we're doing, once again, this is called f prime of x, is what we're trying to find. So this would be the limit as delta x goes to 0. All right, so first it's f of x plus delta x. So that means everywhere I see an x, I'm going to plug in x plus delta x. Okay, so that's f of x plus delta x minus f of x. Now, here's a very important part. When we do minus f of x, we have to subtract this entire function, which means this has to be in parentheses. If you notice at the end that you aren't canceling correctly or something, this is the first thing to check. If you don't show this, sometimes people end up doing the algebra right, but they don't show this, you will lose points, okay? So just like I said, we're very, very picky with this. Okay, so now it's just time to do some simplification. So once again, I'll FOIL this out, or multiply this out. So this will be x squared plus 2x delta x plus delta x squared minus 5x plus 5 delta x minus 4x squared plus 5x. Make sure that gets distributed. Okay. If you want to use h's here, once again, feel free. It does get a little annoying to use delta x. The only reason why I'm using delta x is that in our textbook they use delta x. I have used textbooks where they use h, and also I think in delta math they use h. It's the same thing. Okay, so don't be thrown off by that. Oh, and I made an error here. So negative 5x, and this should be minus. Good thing I caught that. All right, so 4x squared, we got to distribute this 4 plus 8x delta x plus 4 delta x squared minus 5x minus 5 delta x minus 4x squared plus 5x. Now, if we've done this correct, once again, every single term that doesn't have a delta x should cross out. So we have 4x squared minus 4x squared. Okay, so that's gone. We have negative 5x plus 5x. And that looks like we've done our job. So now we can factor out our delta x. So now the limit is delta x goes to 0. This is going to be delta x factored out, which is going to leave us with 8x here, plus 4 delta x, minus 5, over delta x. And of course, the delta x's will cancel. We're left with the limit as delta x goes to 0. 8x plus 4 delta x minus 5. And now I plug in the delta x for 0, and I get 8x minus 5, and that is my derivative function. So we would label that as f prime of x equals 8x minus 5. Now what that does is I can find the derivative of any value at any particular point. So now if I wanted to find what the derivative is, or what the slope of the tangent line is at 2, I would do f prime of 2, plug that in, I would get 16 minus 5, which is equal to 11. Okay. All right, so now we're going to look at what is called the alternate definition of derivative. Okay, we're going to do what is called the alternate definition of derivative. The one thing to remember about the alternate definition of derivative, it actually does not work as a function. You can't use it to get the derivative function. You can only use it to get the derivative at particular values. One of the things is, when you're asked to do definition of derivative and you're given a value, this is actually much, much easier than doing the other form of the definition. So basically what we do is the same thing, except instead of doing c plus delta x, we just do two values for our secant line, c and x. Well, I guess not two values. C is a value, x is a variable. So this will be f of c for output, and this will be f of x. We start off the same way. We're going to do f of x so we're going to start off with the slope of the secant, f of x minus f of c, rise over run. And instead of doing the delta x way, we're just going to limit x to c. So that's going to end up giving us the same sort of mechanism. It's exactly the same mechanism. It's just a little bit easier notation. So f prime of c is equal to the limit as x approaches c. Now I'm going to return to our first problem. If you remember, we wanted to find f prime of 1. Okay, that's what we wanted to find. And we were given the function f of x equals x squared minus x plus 1. Okay, so let's say I wanted to find the slope of the tangent line at x equals 1 to this function, and I had to use a definition of derivative. This actually would be much easier, which I'll show you here. So we want to find f prime of 1. So this is going to equal the limit as x approaches 1. Okay. The function as it is, so that just write the function. Right, so f of x minus f of c. So f of c is just plugging 1 into this, and once again we get 1. So this is just f of c, and this is f of x. Okay, above. Over, and then x minus 1. Now, real simple, you know, if you remember before we had all those lines, this actually works out quite nice. So this gives me x squared minus x over x minus 1. This goes back to something we were doing quite a lot in chapter 1. We have a 0 in the denominator. We have to figure out if we can remove it. Of course we can, because we can factor the numerator. Okay, still, we're doing definition of derivative. Make sure you show all parts, all steps. And of course the x minus 1 cancels. And now I'm just doing the limit as x approaches 1 of x, which is equal to 1. And you can return to that first problem. That's what we got last time. Okay, so that's the alternate form of the definition of derivative. Notice the mechanism is exactly the same. It's just different notation. You have 2 points, slope between 2 points of the secant line. We limit those 2 points together using the limit as x approaches c here. okay? And that gives us a tangent line. Keep in mind, this method only works if we have a value in mind. It will not give us the derivative function, okay? Now, this definition of derivative is actually what we end up using to discuss something called differentiability. So let's talk about that. Okay, so like I said, we're going to talk now about differentiability of f of x at x equals c. Differentiability just means does this have a value for the derivative at a particular point? In other words, is there a value that represents the slope of the tangent line? And so there's a few things to look out for here, but basically the discussion is, does this limit exist? So we use this alternate form of the definition of derivative because it's the easiest sort of wrap our brain around. So does this limit for the definition of derivative exist? In other words, does this equal a real value L? Not infinity, which we'll discuss in a second, or negative infinity, but a value L. Okay, so there's basically three things we have to watch out for to ensure this exists in order to say a function is differentiable. Okay, and it basically comes from just analyzing this. First of all, okay, f must be continuous. If f isn't continuous, for instance, if we have a hole, this thing isn't going to exist. We're not going to have our f of c. We won't have our limit. So, first of all, f must be continuous at x equals c. So we talked about continuity in chapter 1. If we want to talk about why it's not differentiable, we first check to see if it's, or if we want to talk about whether or not it's differentiable, the first thing we see if it's continuous. If it's not continuous, even if it has a hole, end of story, it's not differentiable. The next thing is, okay, well, of course, if this limit exists, right, that means the limit as x approaches c from the left of f of x minus f of c, all right, has to equal L, which is equal to the limit as x approaches c from the right of f of x minus f of c over x minus c. So the slopes essentially from the left and from the right have to match, and I'll show you what that looks like if it doesn't. Okay, and then finally 3. Well, what if this thing goes to infinity? And we'll talk about why that is. You guys probably remember from Algebra 1 that if I have a vertical line, that line exists, I can write an equation for it, x equals some value, but it doesn't have a slope because you would essentially have something that has a rise of some value over 0, which is nonsense. So no vertical tangents. In other words, we can't have a scenario where the limit as x approaches c of f of x minus f of c is equal to plus or minus infinity. And by the way, this goes along with what we were saying in chapter 1. We don't think of infinity or negative infinity, even in the context of limits, as being a value that actually exists. Okay, so let's take a look at some examples of why these would break down. Okay, so I have this written up here. This is definitely something you want to get down. We would say f is differentiable at x equals c if the following conditions are met. All three of these things have to be met. And by the way, when you go through this, go through this in order. And once again, what it means to be differentiable is essentially f prime of c exists. It has a tangent line at a particular point. It has a value, let's say. Okay, it can still have a tangent line, but it might be the slope doesn't exist. Okay, so I'm going to give you a couple examples. First of all, the first one's obvious. Anything that's not continuous. So for instance, if I had y equals 1 over x, right, this thing looks like this. By the way, this isn't a vertical tangent, this is a vertical asymptote. All of a sudden people get confused with these things. So if I gave you this function, we would say it's not differentiable at x equals 0 because it is not continuous. End of story. So that one's an obvious one. And that can be any type of continuity issue that we talked about. Okay, the one that's less obvious, so we need to talk about something that's continuous but not differentiable. So the easiest thing to talk about here is y equals the absolute value of x. Y equals the absolute value of x, right? So it's an easy one to find slope. So this has one trouble area. What we want to realize is as long as our values are positive here, our derivative, the slope of the tangent line, will be 1 for all values. Okay. By the way, if it's a linear thing, the derivative is that value. I know it connects in an infinite number of points, but we'd still say that's the slope of the tangent. And then anywhere where the values are negative for x, we're going to have a slope of -1. So we would say this is not differentiable at x equals 0. And by the way, these both just happen to be at x equals 0. They could really be anything. Because the limit, as x approaches c from the left, of f of x minus f of 0, excuse me, this should be 0 from the left. We have a value here. X minus 0. So from the left, our slope is -1, which does not equal the limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0, which is equal to 1. So the limit of the derivative from the left, the slope from the left essentially, does not match the slope from the right. Another way of saying this is a curve must be smooth in order to be differentiable at a particular point. If it has sort of a sharp turn or a jagged edge, it would not be differentiable. And the final thing is, and if you want to investigate with this, otherwise you can take my word for it, let's take the function y equals the cube root of x. Y equals the cube root of x. If you graph this on a calculator, you're not going to see it. It's going to look something like this, and you're going to say, hey, that's fine. But the reality is, as you zoom in and zoom in, if you keep zooming in on that value at about x equals 0, what you're going to see is this thing actually goes vertical for an instantaneous point. It only goes vertical for a point. So if you're sitting here going, oh, well, that means it's not a function. No, it's just that one point it goes vertical. So at that one point, it goes vertical. So what that means is the slope at that point does not exist, just like we talked about from Algebra 1. So we would say this is not differentiable at x equals 0 because it has a vertical tangent. In other words, from the left and right, so if we were doing 0 from the left, this would be infinity. From the right, that would be infinity. It's not a value. It's not differentiable. Okay, so that is it for section 2.1, the definition of derivative. The big thing with this is make sure you show all of your algebra step by step.